Hello everyone, this is Aon Safdar from National University of Sciences and Technology, Pakistan, and I'll be presenting our research paper titled MoDLF, a model-driven deep learning framework for autonomous vehicle perception. This work is supported by the Higher Education Commission of Pakistan through the NRPU MRED project. So let's start with the introduction. Modern vehicles are extremely complex embedded systems that integrate software and hardware from a large set of contributors. Modeling standards like EastADL have shown promising results to reduce this complexity and expedite system development. However, these existing standards are unable to cope with the growing demands of the automotive industry. A typical case in point being autonomous vehicle perception. So what is AVP? Autonomous vehicle perception is an application area of computer vision where deep learning architectures are being increasingly used for critical computer vision tasks. However, the existing modeling standards being used in the automotive industry are unable to manage these CV tasks at a higher abstraction level. Consequently, system development is currently accomplished through modeling approaches at a higher abstraction level, while the CV features are implemented in isolation at a lower abstraction level and then integrated into the main modeling-based system development flow. This significantly compromises productivity due to integration challenges. So why the model-driven approach? Object detection, recognition, semantic segmentation, etc. These are key computer vision tasks in AVP, and they are required to be performed with the overriding constraints of real-time inference and using the limited hardware capability on board autonomous vehicles. To achieve this, the designers of AVP strive to develop deep learning architectures. This is mainly done through deep learning architectural exploration and extensive experimentation. Contextually, deep learning exploration refers to the changes to the structure of layers, weights, biases, and activations that define the learning algorithm. As a result, we have cutting-edge deep models that are rapidly evolving from specific platforms. The performance of deep convolution neural networks for AVP has improved tremendously, but the increased sophistication is at the cost of increased complexity and increased development time. Another challenge is the lack of cross-platform interoperability, as the implementation of deep convs is commonly done on mutually exclusive development platforms or language ecosystems. For example, the leading proprietary MATLAB platform and the open source community driven Python platform with its various flavors, they have very limited interoperability, and that too with complex pipelines or intermediary frameworks such as the ONXX or the neural network exchange format. So platform specific code implementations are required to be developed separately. This reduces the implementation potential of these rapid innovations due to increased deployment fragmentation. So in a nutshell, platform independent modeling is not currently available, and there is increased complexity due to low level code implementations for the CV tasks in AVP. And finally, as highlighted earlier, there is lack of integration with model-based vehicle system development flow. So what we propose is a framework that allows platform independent modeling of deep convolution neural networks, and being able to do that at a higher abstraction level in order to reduce existing design complexity while supporting integration with modeling based vehicle system development flow. We also aim to provide an intuitive modeling environment with the capability of code generation for a low code or no code solution to promote rapid innovation and to promote cross-platform interoperability. This is the high-level view of our development methodology for MoDLF. We started off with domain conceptualization, where we conceptualized and amalgamated the core concepts related to deep learning, computer vision, autonomous vehicle perception, and various model-driven approaches used for automotive system development. After conceptual integration, we leveraged OMG's MDA standard using the Eclipse modeling framework to develop M2 level E-core meta model. In the second stage, we instantiated the meta model to develop M1 level system models, where we first created a customized tree editor and then converted it into a series-based graphical editor. There onwards, we use the Accelio model-to-text transformation language for code generation for two platforms, MATLAB and Python. For the validation part, we performed two case studies, one on recognition task and other on detection task using benchmark datasets. And modeling and code generation were done using the MoDLF artifacts, and the results were analyzed and improved. So starting off with the explanation of our M2 level E-core meta model. Our proposed meta model defines key concepts as meta classes and their associations required to model deep learning architectures for a wide variety of computer vision tasks. Starting off with the root meta class. The DLF is the root meta class and represents a deep learning system. It can be composed by EastADL and AutoSAR meta classes for integration with the existing development flow of automotive systems. The EastADL and AutoSAR meta classes are EMF implementations of their existing meta models. It is pertinent to highlight that DLF is not exclusive to automotive systems, and it may be composed by various other systems for domain-specific computer vision challenges. Moving on to CNN model, it is composed by DLF and it represents the deep learning architecture. The classes enclosed in the green box are related to dataset related concepts, in which the dataset meta class, which is an abstract class, is subtyped by training and testing datasets, and it further composes image and its related label. A CNN model composes layer, which is the main construct of any deep convnet. A layer has certain attributes such as name, activation, batch normalization, regularizer, its rate, etc. And this class is subtyped by different classes. First of all, the concrete meta class of input layer, which represents the input image with its attributes of width, height, and channels, and is also subtyped by the abstract class of convolution layer, which has attributes of kernel width, height, stride, and padding, all concepts related to the convolutional operation, and it is subtyped by various convolutional layers. Thirdly, the linear layer class, which is a abstract class, and it is subtyped by the dense or a fully connected layer class and an output layer class. There are various operations that can be performed on layer, and these have been subtyped by the respective concepts. There is a concept of transfer learning and model concatenation, in which the pre-trained models are used for specific use cases. So the constructs for those have been provided here. And finally, a model has to be trained and tested according to various parameters, which are the hyperparameters, and these have been subtyped under the training parameters, as you can see: epochs, objective functions, optimizers, learning rate, etc. So these are all the hyperparameters which have to be experimented with in order to ensure optimum learning of your model. As part of the MoDLF framework, we have developed a comprehensive tool set for developing deep learning architectures, starting off with the Serious Graphical Editor. So we use the series specification editor to create diagram area elements that includes relation-based edges, which map to our associations in the meta model, and containers and nodes that map to the composing and other meta classes of our meta model. For the sectionized iconized palette, we use various creation tools to create these containers, nodes, and edges. So this is our main modeling environment called Moog. It has three main parts: an iconized palette, which contains the M2 level classes corresponding to our meta model. These can be dragged and dropped on to the drawing canvas to create their M1 level instances and these instances conform to the vocabulary of the M2 level meta model. And finally, the attributes can be of the M1 level instances can be set from this properties palette. So moving on to the M2 text model to text transformations. The essence of MDA is realized through transformations where platform-specific codes are generated from the developed models through model to text transformations. So this reduces the development time through a low code or a no code solution. We achieved this with the help of a templates-based approach, wherein the text generation was done through the text templates parameterized with model elements. A template comprises a text template with placeholders for data that is extracted from models. So these placeholders are essentially expressions specified over the meta model. And then the generated values can be converted into text expressions using an expression language. For our purposes, we use the Excelio expression language. As you can see here, we have the equal meta model, its corresponding M1 level model. And from there, we have these placeholders, which are mapped to our transformation rules through to the entities of our M1 level model. And according to that, our code is generated for Python and MATLAB. All of these artifacts, the meta model, the graphical editor, and the code generator are publicly available, and they are supported with a very elaborate user manual and a video demo of how to use them. Studies. For the first case studies, we used the traffic sign classification problem using the GTSRB dataset with 43 classes. And the goal was to design a lightweight CNN architecture for embedded systems onboard AV. And the method we used was architectural modification to lean at 5. So initially we modeled the lean at 5 on our graphical editor, and then we used various modifications to improve upon it. We used that model to generate code using our transformation engine, and we generated MATLAB code for them. And the results showed that we improved the accuracy of recognition, and the results are as flashed. For the second case study, we chose a very challenging data set for object detection in thermal images. It is called then we said with 4 classes, and the goal was to have object localization in a highly cluttered environment. And the method used was VGG16 with a custom regression head. Once again, we used the basic model construct, and we used the pre-trained VGG16 with on ImageNet dataset, and we took off its top layers and added a regression head, and then we trained it. All this was modeled once again on a graphical editor. Then we generated this time code using our transformation engine for Python, and the results showed that we achieved up to 99.1% accuracy for object localization. We have drawn comparison of MoDLF with notable model-based deep learning solutions, namely MATLAB Deep Learning Toolbox. It is a proprietary solution for rapid prototyping of deep conv nets, but it can only generate MATLAB code. Veka is open source, but it is geared more towards machine learning solutions rather than deep learning solutions. RapidMiner with its extension H2O is also proprietary, but it has a no code generation capability. And a more pertinent comparison is with DeepForge, which is another model-driven solution for deep learning exploration. So DeepForce is built upon WebGME, which is a parallel MDE standard and leverages the GME standard of model integrated development. It is a robust cloud-based design studio that offers collaborative development with reusability and extensibility. However, considering integration, the leading eStadial modeling toolchains are based on EMF. So integration of MoDLF with these toolchains is straightforward as opposed to GME-based tool. Finally, a few limitations. Currently, MoDLF supports only basic CNN constructs, while advanced CNN constructs are yet to be integrated. OCL-based constraints can be added to enrich the meta model for analysis at design time. And currently, the transformation rules, it's a non-exhaustive set and can be further improved upon. With this, I come to the end of my presentation. I thank you for patient listening.